I want to talk about two things today. I want to talk about the inadequate technique and then give you some thoughts on homework set 9 and build on some of the stuff that I kind of started to scratch at the blackboard, and I worked up something last night with some models that I thought would be really useful for some of our thinking and tie into some of our conformational analysis. So let's talk about the inadequate technique first. It stands for incredible, it is a stretch, incredible natural abundance double quantum experiment and what it is essentially a CC cozy. So it's essentially a CC cozy. And what's so incredibly powerful about this technique is it means that you really can stitch together any carbon skeleton with it. And what's inadequate, of course, about it is the amount of C13. So I'll say very powerful, but requires lots of sample and lots of time. So by lots of sample, I mean like 100 milligrams. In other words, if you're dealing with some rare natural product where you've isolated a couple of milligrams, right now it's essentially out of grasp. If, on the other hand, you have some side product in a reaction and you think this is key, to optimizing a reaction, maybe not a late-stage intermediate in a synthesis, but maybe in a methods project, and you're trying to suppress something, and you can get yourself 100 mgs, and you just can't get a handle on it any other way. This may be a way. So, I mean, the killer on this thing is because it's a cozy-like experiment, what you're relying upon is having a C13 next to a C13. And since the probability of having a C13 at either position in a molecule is 1%, the probability of having both of those is 1% of 1%. In other words, 0.01%. And that really is the killer, because it means, carbon, you've done carbon on strychnine. We loaded up the sample tube. And, it's like 40 mgs of strychnine in the sample tube, and it's pretty quick. But if you're talking about having two C13s next to each other, your signal to noise is going to be 100 times lower. Now, remember what I said. If you're talking about a particular signal to noise level, if you drop your concentration of sample by a factor of 10, you've got to collect data 100 times longer to get the same signal to noise ratio. If you're C13, if you're dropping to 1% of 1%, then you're talking about 100 times less sensitive. So it really can be killer. Now, there are tricks that get played, and they're not fun if you've got a compound that you really want to get back. So one of the tricks is that you often can add chromium 3 to increase relaxation. Remember how the quats are always small. The quat carbons are small because their relaxation time is typically on the order of milliseconds, and you're pulsing every couple of seconds. So most of your magnetization is not returning to the z-axis. So you can add a paramagnetic compound, a metal ion, that promotes relaxation. That's going to reduce the relaxation time, so the magnetization returns to the z-axis. That'll help you a little. help you out a bit. But we're often talking many hours or days. Of NMR time. Now, I will say this, the cryoprobe, and we haven't really sat down and tried this thing with the cryoprobe. Maybe Phil has, maybe somebody has. So the cryoprobe instrument is super, super sensitive because you're cooling the coil in the probe and reducing the amount of noise. It's not increasing the amount of signal, but if you reduce the amount of noise, you increase the signal to noise ratio. The cryoprobe is like 5 times or 10 times more sensitive than a traditional probe, let's say 5 times. So that's going to buy you a lot, because remember, I said 5 times more sensitive, 5 times more signal to noise can translate to cutting your experiment time down by 25 to get the same. I'm sorry, no, 5 times will cut it down by 5. But that's still, can help you out. So again, I'd urge you to think about this. I want to walk us through one example and then get you started. We have 2 homework problems that have inadequate, and I want to get you started on one of them. So there are 2 variants of the experiment, just different variations in pulse sequence. One of the variants is like a cozy in terms of how it looks. I'll show you both of them in terms of how your axes look. So it's just like carbon on one axis, carbon on the other axis, and you just correlate like you would in a cozy. The other is with what's called a double quantum axis. And I'll show you what that is. All right, so I think what I'm going to do is pass out an example, and we'll actually piece together the whole structure on this thing very, very easily and quickly. Oh yeah, there are extras over there. Just sweep them back to your right. Everyone have one? Great. All right. So unfortunately, because this experiment really is a tour de force in terms of instrument and so forth, most of the examples that you find out there are not worthy of the technique. They are didactic examples that sort of are nice, but it's like, okay, we could have done this without bringing such a powerful technique to bear. A lot of the examples and handouts I've been giving you are from a book by Koji Nakanishi, who's a natural products chemist. And basically, he put together various nice little sort of 2-page handouts in the book on various spectroscopic, various NMR techniques. They were recorded on a 400 megahertz machine. So this is recorded on a 100 megahertz carbon NMR spectrometer. So nothing, and they're kind of old, so it's nothing near as powerful as what you have downstairs with the cryoprobe. So what we have here is an example of an alcohol, and it happens to have, I'll give you a formula here. It happens to have a formula C10H20O. And so you'll have 10 unique resonances in the carbon spectrum in this molecule. And what we're going to do is we're going to stitch together the whole structure really painlessly, really effortlessly, and really mechanically with this inadequate experiment. So I'm going to number my 10 resonances, 1 to 10, just like we always do. These letters by the resonances, remember I mentioned before that before the depth experiment was developed, there was an older technique called off-resonance decoupling. So when you collect your carbon, normally it's proton coupled, meaning proton decoupled, meaning you're irradiating the protons, there's flipping spins very rapidly, so you don't see any J coupling to the carbon. But with full coupling, all of your peaks are very heavily split because you've got your one bond coupling, which splits with like 125, 160 hertz coupling, splits your lines into doublets and triplets and quartets. But you also have on top of that your two bond and three bond coupling, which means every peak is heavily split into many, many lines. So it becomes like a quartet of triplets would be, say, what you'd see for the methyl peak in ethanol, and the lines are very small. In the off-resonance decoupling technique, you're partially decoupling. You're applying proton energy to flip the spins of the protons, but you're not doing so at the exact right frequency. So you're doing so slowly. So your multiplets collapse down, and you don't see your 2 and 3 bond couplings, and you see just your 1 bond coupling. And instead of having like a quartet spread out with the lines 125 hertz apart, they're just like 10 hertz apart. Anyway, that older notation, which isn't used anymore, has stuck around. So a doublet means CH, a triplet means CH2. You'll still sometimes see this when people report depth data. Sometimes they will report it as D and T for no particular reason, D meaning CH, T meaning CH2, Q meaning CH3, of course. And the rest of these are CH3s. So, okay, so our molecule contains some methyl groups. It contains some methylene groups. We have this one methine group down here at 70 parts per million. I said we're an alcohol, so obviously, this carbon, a 70 is right in the range where you'd expect a carbon connected to an oxygen. So obviously, that's going to be the one connected to the oxygen. All right, the double quantum axis is a diagonal, and what you're seeing, each of these pairs corresponds to 2 carbons that are coupled to each other. And you'll notice that each one appears as 2 little lines. What are those 2 little lines? And doublet, and from the carbon-carbon splitting. Yeah, so you're seeing the carbon-carbon splitting. Remember, carbon has a much smaller magnetogyric ratio than protons. So the carbon-carbon coupling constant, the 1 bond J1CH, is going to be smaller than a typical carbon-proton 1 bond coupling. So you can kind of see this was done at 100 megahertz. This is done on 400 megahertz spectrometer. So each of these tick marks is 100 hertz. And you can see this spacing is maybe like 30 hertz. So that's your J1CC coupling. All right, here's how the double quantum axis works. Each of these coupled peaks, they come in pairs, and there's a diagonal that goes between them. And so if you look, all of these pairs go right around this diagonal. I haven't split them exactly down the middle. I tried as close as I could. So this pair is centered on the diagonal. This pair is centered on the diagonal. This pair is centered on the diagonal. This one on the diagonal. This one on the diagonal. This one, and so on and so forth, up the double quantum axis. This is really important because in inadequate, you're pushing the signal to noise level, which means you will have noise in your spectrum, most likely. This one, as I said, this is a 10-carbon compound in a demonstration experiment, so there isn't a lot of signal to noise in it. But if you're doing this technique, you're basically going to be sitting on the spectrometer, running like an overnight block, coming in the morning, maybe doing this on a weekend, hoping when you Fourier transform and process your data that you can get off the machine, but maybe you've signed up for all of Saturday, you know, Friday night through all of Saturday with the idea that if you need more time, you can get it. And so you will see noise. I mean, we see noise in our other spectra, but some of that's artifacts rather than noise. You will just see basement noise here. But what you want to be doing is saying, yes, I can see a pair of peaks, and you know where your pair of peaks is going to be. In other words, it's not going to be a pair here and here. It's not going to be a pair here and here. It's going to be a pair centered around the double quantum axis. All right, so let's start to build up our structure, and we can do so very mechanically. I'm just going to trace my pairs, and you can start anywhere. I'll just start here, and we'll just sort of get our cross peaks. And so this pair becomes 6 to 10. Okay, so 6 is a methine, so I'll draw that as C6H, and it's coupled to C10H3. So we're well on our way to building up our structure. Okay, so let's continue. And so I will just select my next pair. And so that is 6 to 9, so that's good. C9 is another methyl group, so C9H3. And then I'll continue. We have the next one looks like 5 to 8. I could start to draw, was that right? 5 to 8, yep. So that's over 5, and that one's over 8. So I could start to draw out another chain, but I'm just going to sit tight for a moment because I'll figure out where to put everything in just a moment. The next one looks like 4 to 7. The next one looks like 4 to 5. So as soon as I can figure out where 4 is, I'll be in pretty good shape. Next one is 2 to 7. And the next one is 2 to 6. Okay, that's good. Now I've got a lot of information I can start building. So 2 is a methine, so I will say C2H. And let's see, 2 connects, I think the other one I got is to 7, which is a methylene, so that's C7H2. And it looks like we have 4 to 7 over here, and 4 is another methylene. So C4H2. Okay, so I've used up the 2 to 7, the 4 to 7. Okay, it looks like I have 4 to 5, and 5 is a methine, so C5H. Okay, and what else do I have? I guess I still have 5. 5 goes to 8. I haven't used him up, and 8 is a methyl. So C8H3. And let's see, I think now I've used all of those up. So let's see what I have next on the list here. So I have 3 to 5. So that's a methylene. Is that?
No, we're just saying it makes it too easy.
Yeah, isn't it? It just makes you want to run this thing until it takes you a day. Well, the great thing with this course. Okay, so I think what was happening on the 500 was people were getting antsy over orals. So if you want to sneak back there now, I think I think, trying to leave a few blocks of time, but you've got this free NMR time on this course here, right? No one's going to be around Thanksgiving, right? So, you want to run an inadequate on strychnine on the cryoprobe. All right, so let's see, where are we going here? Okay, so we've got, that looks like 1 to 3. It
doesn't make like center to center. It's kind of like the 3 kind of elevate us from the 1.
What's that?
The carbon 3. It doesn't go straight. Does that matter?
Does it? You mean I haven't drawn a straight line here?
No, because when I draw a straight line, it's kind of above.
One of the dots slightly higher.
Yeah.
Is it?
Yeah.
Let's take a look here. It's hard staring into this thing, so let me slap a grid on this. They look like, if you look at the grid lines, they look like they line up. I think I've put the grid on the axis here. I think everything's pairing up. They look like they're pretty well lined up. All right, so 1 to 3. Now, one is that one that has to bear the alcohol. So C1H, that has to be the one with the OH on it. And our last one here is 1 to 2. And so the whole structure gets built up. Now, we still don't have issues of stereochemistry answered at this point. So we have 3 stereocenters in the molecule, and so if you were trying to figure out what the structure was at this point, of course, you can't get the absolute stereochemistry, so you have to get the stereochemistry of 2 relative to the remaining third one, and that would be from things like coupling constants and NOEs. In fact, this is a cyclohexane ring, so it fits in very well to all the models and issues we've dealt with cyclohexane rings. Anyway, that's largely what there is to the experiment. And as I said, very, very powerful, very tempting and teasing because, of course, it is so powerful and yet very frustrating because it isn't something that you can pull out except in heroic circumstances. So this is the handout from Nakanishi's book on the technique, which, what I like about his book is he always has just sort of a short little paragraph on the technique and then an example here. So this particular molecule happens to be the monoterpene menthol. And so as I said, there are two basic flavors of the experiment. He's demonstrated both of them. I simply took the one on the left here and used that for our example here. So this is the one with the double quantum axis. You can see the pulse sequence. You notice it's all a carbon detected experiment. And then you have the version that's the cozy-like version. And your cozy-like version basically just traces up and over just like you would with a cozy.
When they do natural products chemistry, do they normally have enough of the natural products
No.
to do this?
No, absolutely not. The natural products chemistry these days is often pushing the envelope. So Phil Cruz is a great example of this. And in fact, he has a really good NMR book. The only thing is, in my opinion, it's more oriented toward natural products chemists rather than toward, say, synthetic and other sorts of chemists who build molecules. So when you're doing that, you're often like collecting 10 kilograms of wet sea sponges, getting a kilogram or 2 kilograms of dry sea sponge, fractionating it by extracting with, say, methanol and chloroform, and then chromatographing and isolating bioactive components and running various chromatographic techniques, in the end getting a few milligrams of compound, sometimes less than a milligram. So one of the frontiers in NMR right now is really small probes and probe volumes so that you can concentrate your sample in a very small space and get enhanced signal-to-noise ratio with small samples. In a way, a 5 millimeter NMR tube, what's sort of this typical standard, is a big sample in the sense you're putting a lot of milliliters in there, but it's a very convenient size for preparative chemistry. It's just that by the time you're dealing with a really late stage intermediate, say in a long total synthesis or a natural product, it may not be enough. So I want to get you started here on, were there other thoughts or questions on this, I think? Yeah. Somebody? Why are the methyls on the isopropyl not equivalent? They're diastereotopic. Whenever you have a stereocenter in the molecule, an isopropyl group and a methylene group are going to be diastereotopic. If they're very far from the stereocenters, they may be coincident. They may show up at the same place, but they are always topologically diastereotopic. So if I had like a 5-carbon, just a linear chain with an isopropyl group at the end and a stereocenter way off 5 carbons away, yeah, chances are those two methyls would show up at the same position. But if it was just a couple of carbons away, probably at least in the carbon NMR, which is more sensitive, they'd show up at different positions. All right, I want to give you so one of the things I wanted to do, this last problem set really is very, very beautiful, and we get a lot of stuff in it, but it's also pretty tough. And I wanted to spend just a couple of moments getting you started on several of the different problems and also talk about some conformational analysis and stereochemistry that's germane to them and actually was germane to the last problem set as well. All right, so this is one of the problems from the problem set. And if you look at this, I want to keep this fun for you. You get a low-res mass spec. You're going to be able to basically infer the molecular formula. It's just a carbon, hydrogen, oxygen compound. You're going to be able to figure out the molecular formula. There are 9 resonances in the C13 NMR, and yet if you look at it, you'll see something interesting about the proton NMR. If you just work your integrals, you'll see 2, 1, 1. What do you do? You usually measure with a ruler, or you can slap a grid on it if you're feeling lazy for measuring your integrals and you don't want to be bothered drawing lines with a ruler. So my preferred way, if you can get a hydrogen count, is always to add up all your integrals here. So if I was adding this up, it'd be like 1.7, 1.7, 1.7, 1.7, and then what are we at? We're at about 9.3, and then divide by the number of hydrogens. But if you're being lazy, you can say, okay, because otherwise you're putting all that weight on 1.7, and if the 1.7 is really 1.5, then you come to a peak that's like 9 hydrogens, and that error of 10% is going to make your 9 hydrogens be 10 hydrogens or 8 hydrogens. But if you're pretty good here, you probably can get away eyeballing it as 1 and 6, right? So you're probably going to be well on your way to a molecular formula here. Is that right? Oh yeah, we've got this guy over here. So we've got 6, 8, 9, 10, 11, and it looks like we've got something here as well. OHs and the like are always hard to integrate. In part, they're often broad. Often the integrals aren't so accurate because phasing of your integral becomes really, really important. This has got to be some sort of OH. Some sort of OH over here. All right. With 6, you might even think about what that means in terms of the structure of the molecule. I'm going to take us on to the inadequate. And honestly, you can pretty much just by inspection with the inadequate put the thing together, and then you're going to have to use your head a little bit to think about what's going on. All right. So they give you two spectra, the spectrum and then an expansion of this crowded region here. So this is your inadequate, and we can go ahead and do 1, 2, 3, 4, 5, 6, 7, 8, 9. You can identify your double quantum axis in addressing this spectrum. Should have 10 carbons. What? Did I miscount? This here?
That's the expansion one. 9 is actually 2 carbons. It shows up as 2 methyls. It shows up as 1.
Yeah, so that's what we were seeing with the 6 hydrogens. So what is that telling us about the 6 hydrogens? Probably not diastereotopic, probably some sort of isopropyl group in there. Yeah, so, okay. So I want to point out a couple of features. So one feature is, all right, so like here, for example, you can pick up 8 and 9, and it's right across the double quantum axis. And here, for example, you can pick up, they've even drawn a line for you, you can pick up 8 and 3. But what can you tell about this and this spot? And now I've just circled it so badly that I've circled over it. What can you tell about those two? What? That can't be. It may be an artifact, it may be noise, but they're not a cross peak. Because they're not spaced on that double quantum axis. So some type of artifact, but not a product of the double quantum axis.
Also doesn't look like a split either. Is that maybe elusive? Oh no.
You know, it is something off of. So what's interesting here? So this is our carbon doublet. You see that that's your CC coupling. But here, these are singletons. These are spots. They're not doublets. So whatever it is not J1 CC coupling. We have a spot under here. Here, let me transcribe my lines. So it's 1, 2, 3, 4, 5, 6, 7. So we have a spot under 6, a spot under 7, a spot under 1, a spot under 2, but they are not part of our pairs that we need to consider. And so then, as we continue our double quantum axis here, you'll see that you can just pick up your pairs. So you're going to get your 4 to 7 pair. You'll get your 4 to 5 pair here. You've got a 3 to 6 pair here. You have a 3 to 5 pair below that. a 2 to 7 and a 1 to 6 pair here. And then what's going on over here? That's got to be a 1 to 2 pair. If 1 and 2 weren't giving a cross peak, you wouldn't see a spot here. So even where they're really close, we're seeing a 1 to 2 cross peak. So that's going to, you're all set to go ahead and tackle this on your own. I don't want to.
Do you ever see any type of long-range coupling with this, or is that not an issue?
You know, I think the answer is it could be an issue. Your Pretsch book and Silverstein will give you your J2 and J3 CC coupling, and they're going to be small. They're going to be a lot smaller. We already saw on problem number, on that Santonin problem, that very nice sesquiterpene problem, we saw that darn peak from 4 to 7E, which, by the way, now I've gone ahead and put a note on the problem. So we have seen, in some cases, you can get some longer range coupling showing up. It's surprising. So I wouldn't say never, but it would surprise me. Certainly, if you look at your little paired couplings, that's got to be an indication that it's one bond coupling. I can already tell you, so this molecule has a lot of sp2 carbons in it, as well as some sp3 carbons in it. If you had like sp carbons in it, you could imagine them being, further, even bigger spacing. But I think if you were, and that may be what we're observing here. It might be something that's a long range type of coupling. Honestly, I don't know, but you notice we're not seeing this paired lines here, so that's kind of an indication. All right, I think this and the IR spectrum are going to be enough. You can do a little bit with the cozy on it. You can do a little bit. Take a look at the IR spectrum. There's obviously some stuff going on. This molecule has carbon, hydrogen, oxygen. We obviously have some type of alcohol. We've got some stuff going on here that's interesting, either with carbonyls or double bonds or something. So, what I'll say is, something that's pretty obviously an OH, but then, something interesting. You'll figure it out at this point. All right, I think that's all I want to do on that problem to help you get started. And let's see, what else do I want to do? I think the other thing I want to do at this point is to spend some time talking about some of the issues that I was talking about on the Blackboard in discussion section. I worked up an exercise, and you're welcome either to follow along or not on your computers on this.
I don't mean to digress too much, but when we talk about the example with menthol, if we were to say remove that OH and make a meso compound, those two methods would then become equivalent, right?
If you were to remove that.
See, but then no, it's not.
No. Then.
Because there's still that methyl group. They would at that point become equivalent, yes. However, so meso compound, they're going to be equivalent. But remember, the most rigorous test is always replace one methyl group with like a C13 or a CD3 group, replace the other methyl group, and then ask yourself, what's the relationship of those two compounds? Are they diastereomers or are they not diastereomers? But remember, if those two methyls are interchangeable by a symmetry operation, a mirror plane in the menthol, which they are, then they are not diastereotopic. So plain and simple. All right, so I want to talk about some stuff that is directly germane to the homework. and also germane to last week's homework. And I want to talk a little bit more about this concept of some very, very basic conformational analysis. And this is fundamental to organic chemistry. It's fundamental to Carey and Sundberg Part A as well. It's fundamental to understanding structure. So I was quipping before that I can draw only two things, and everything else I can fake it. And that's really kind of true in the sense if you can do two things, you can do basic conformational analysis on a whole bunch of cyclic, bicyclic, and polycyclic ring systems. So if you understand chair cyclohexane, then you can basically understand an envelope cyclopentane. Cycloheptane has a number of different conformers, but you can basically fake cyclohexane. You can start to figure out, okay, I have hydrogens here and so forth, and you can fake a whole heck of a lot. If you can understand norbornane, if you can understand bicyclo-2,2,1-heptane, and that really is a poor drawing, so let me do a little bit better here. If you can understand bicycloheptane, then you can fake a lot of other cyclic ring systems because you can go ahead and fake, say, a bicyclo-3,2,1 system. This bridge, you notice that embedded in the bicyclo-3,2,1 system, you have, and I guess this is a little bit better drawing, which means I probably should be faking this like this, actually. So you notice you have a cyclohexane embedded in this system, and it's a chair cyclohexane. You can also flip up. If you had a bad steric interaction here, you could flip up. That would be a boat cyclohexane. Can you see your boat embedded in there? And you can go ahead, and if you want to, then you can fake other systems. So if you can fake this system, then you can fake, like, remember we had the pinane diol problem? And you can fake the conformational analysis of this as well in your drawing. And if you can't see this the first time around, the beautiful thing is a few basic models can help you out. And so after thinking about this and thinking that really my own understanding of this comes from sort of playing with models, I figured, well, if something's good for me, it's going to be good for you. And so both on the class materials and the assignments, I created let me shrink this. I created a web page that links to some basic models of all of those structures. And so I created this simple conformational analysis of these structures. So I've hot linked these all to PSE files, to the PyMol files. And I guess what you have to do at that point is you sort of have to open them separately. I've programmed my computer to, let me see if I can turn down the lights here. Let's see, we have a lights button. So, okay, that's going to be a little bit better. Yeah, I've programmed my computer to open these like this. Obviously, I mean, you know exactly by this point how you get, what you're probably some of you are teaching your sophomores to draw the relationship between cyclohexane projection and the three-dimensional structure of the molecule. So of course you have your axial and your equatorial hydrogens on that. But what I was saying about an envelope cyclopentane structure is you can go ahead and basically apply that same conformational analysis to cyclopentane. And so you see I've sort of continued and done half the chair. Now, this brings up an interesting point. Why am I talking about this? Because I'm interested in coupling and being able to identify stereochemistry from coupling, and NOEs and being able to identify NOEs. And one thing, we already had one problem on the homework where we had a cyclopentane ring system. It was that hydroxyproline one where we had to figure out the stereochemistry from the NOEs, and I think it was in part confusing because in the 1D NOE there was non-specific irradiation of the diastereotopic methylenes. One of the points when I introduced NOEs earlier on, and we were talking about distances, and I said, well, you know, on a cyclopentane ring, basically, if you've got a cis relationship or you've got a trans relationship, you know, you're going to have some difference in distance, but it isn't necessarily, if I only saw this an NOE here, and I said, oh, these two must be cis to each other because I'm seeing, 2.8 angstroms will give you a nice strong NOE. You'd be absolutely wrong here. You know, ditto if I were looking at, say, this hydrogen and these two hydrogens. And this is one of the reasons I like these canonical structures and I like being able to play with these models, is it really helps me think about what we're talking about. In other words, you really are ending up having to make comparisons on cyclopentanes and 1-2 relationships.
How do you get the differences?
In pi mole or from NOEs? Oh, in pi mole, it's from the wizard, and there's a measurement for, and it gives you either distances or it's a pull-down menu, and you can get dihedrals and so forth. So remember that coupling constant calculator, and we did it two ways. One was by taking it onto the modeling facility computers and using Macromodel, where it had a Karplus calculator built in, and the other way was a website that one linked to the tetrahedron paper on typical J values with different substituents. So if you just wanted to use the website, you could just get your dihedrals. You pull dihedrals there, you click on the 4 atoms, you go hydrogen, carbon, carbon, hydrogen, you get your dihedral, and you put in your substituents on the pull-down menu on that tetrahedron calculator. Or at least if you're thinking basic Karplus curve, you say, oh, wait a second, 90-degree dihedral, virtually no coupling constant, 170-degree dihedral, well, remember, it's a cosine wave, basically. 170 is going to be a big J value. Now, one thing that's interesting with cyclopentanes is for 1-3 relationships, so let me hide some of these measurements. I'm just going to click on these to turn it off. For 1-3 relationships, you really don't get close trans relationships. Cis ends up, an NOE in a 1-3 relationship, so we're going 1, 2, 3, in a 1-3 relationship, an NOE is pretty darn diagnostic of being cis, because that's 2.7. So here we go in the trans, it's 3.8, and 3.8 angstroms. Remember how I said NOEs fall off as distance to the inverse 6 power. 3.8 angstroms is going to be a very, very small NOE, just a small percentage of what a close NOE would be. So that can be really, really diagnostic. All right, I want to show you at this point a 7-membered ring. 7-membered rings, as I said, can have different conformations, but often you're going to find a conformation that's very similar to this canonical cyclohexane. It's my faking it. And you notice you have 3 hydrogens that are basically axial and 3 that are basically axial here. I've put the methyl group equatorial here on the ring. And so you can start to see, oh yeah, then all those things I was thinking about, like a big J between these hydrogens or a big J between these hydrogens, or a close contact between these hydrogens, is going to apply.
The other family I thought that was really useful, here's our Norbornane structure. These are all minimum energy structures. You know, the clean function, it's generated with molecular mechanics with the MMF force field. So here's the Norbornane structure. If you want to go ahead and see the projection that I drew over there, what I badly sketched out on the blackboard, that's our basic structure. But now you can start to imagine with issues like when we were dealing with the camphor problem, and we were dealing with that issue of, oh yeah, what's the distance of a methyl in the bromocamphor sulfonic acid problem? What's the distance here? I'll even clean this thing up, not that we really need to measure a basic distance. What's the distance for, say, a cis distance, right? Because that was where we had this issue of, is the bromine pointing up or is the bromine pointing down? And you'd be able to look and say, okay, you know, by golly, a cis distance is going to be a nice strong NOE. A trans distance is going to be a much weaker NOE. It also helps you calibrate. So remember, we were dealing like with a methylene or a hydrogen off of there, and you can start to say, oh yeah, I can begin to think about these types of distances as well. So that's why, I mean, this is so integral to understanding stuff. So I'll give you a bicyclooctane, bicyclo-3,2,1 octane structure. And so we've got this. This is, you notice you have your cyclohexane embedded in it. This is what I was talking about. You see your chair cyclohexane embedded in the structure there. So it's sort of just like a chair cyclohexane embedded in the structure. So you can play with that. Here's the bicycloheptane. This you could use as the bicyclo-3,1,1 heptane. This is one that you could use as a template. You did, right? Because you said it was flattened, right? You told me it was flattened. You modeled it, or? Yeah. So this is our pinane diol problem. The other canonical structure so basically, if you get a few simple structures, as I said, you can do so much. The other one that's sort of canonical for understanding conformational analysis in so many natural products is transdecaline, which is basically just cyclohexane with another ring extended on, and it's chair-chair. And cisdecaline is also chair-chair, and here I've drawn it the way you'd get from a projection. And here's your cisdecaline, and it's just a chair, and then we have an axial group and another chair. Last thing I'll do is let me just show you how these fit into a couple of things. So here's our strychnine molecule. You've all modeled this. And you notice on the 7-membered ring, here I'll bring it over. Here you can see the 7-membered ring, even though we have an oxygen in it, even though, let's see, that's a little hard to see. There you go. Even though you have an oxygen embedded in your 7-membered ring, you can see this chair-like structure. Even though you have a double bond in it, an oxygen in it, you've got your 3 sort of axial hydrogens. So that's going to influence your thinking as you start to assign your protons and assign your stereochemistry. The problem that from the previous problem set that I presented as a demonstration where I was talking about and drawing things on the blackboard. So you notice this, you've got your chair cyclohexane, your angular methyl. Your angular methyl was the one that gave the NOEs to these axial protons. That helped us assign our stereochemistry.
You had your NOEs, like this hydrogen was one that was a real, I guess this was the real linchpin, because this one was the hydrogen that gave the NOE to the methyl, gave the NOE across here, gave the NOE here. All of those are short distances. All of those are just, two basically van der Waals contact or thereabouts. So all of those are nice, short, strong NOEs, 2.6, 2.2 angstroms. The other one, which was a little messier to see when we irradiated the methyl and we saw the NOE over to this other hydrogen, again, that's sort of gave us our stereochemistry here. And you notice this structure here with the cyclohexane and the 5-membered ring is basically what I'm talking about with the transdecaline. And then your 5-membered ring, the conformational analysis, is essentially that envelope cyclopentane. So you understand transdecaline, you understand envelope cyclopentane's relationship to cyclohexane, to chair cyclohexane, and you can fake the conformational analysis of this system, and then you just sort of have a double bond coming off kind of at the middle position here, equatorial position here, and you have that last ring. So there's a lot of power in being able to model and analyze structures. All right, well, I think that's where I'd like to end things up in terms of discussion. Go and attack the homework problems. These are some of the prettiest and most satisfying problems of the course. On some of them, if you make a model, it's going to be of the actual molecule. It's going to be incredibly enriching when you start to get your stereochemistry and get your diastereotopic assignments. And you can start with those PSE templates if you want. Oh yeah, last thing I'll mention. All right, actually, I will skip it. I will leave you on your own for one last point. You will figure it out. You want it?